Hello everyone. Welcome to the presentation on our project for VLSI Circuits and Design 2 laboratory course. We, the members of Group 2, are going to provide a brief overview on our project, front-end and back-end design of data encryption using DES algorithm. Data Encryption Standard, abbreviated as DES, is a complex encryption algorithm published by National Institute of Standards and Technology that uses a 16-round FISL structure. We provide two inputs here, a 64-bit encryption key and a 64-bit text. The result will be a 64-bit ciphertext. DES utilizes subkey length of 56 bits in each round, and the total number of rounds is usually 16. To make the 56-bit subkey from 64 bits, we apply the key discarding process. Here, the rightmost bits are eliminated and permutation is done in a certain serial. On the other hand, the plain text goes through the initial permutation step as shown here. We put 58 bits at the first place and so on. Then it is divided into left and right part, each with 32 bits. Following the 16 rounds encryption and final permutation step, we get the ciphertext. We can find the blocks for 16 similar rounds here. In the first round, the right part goes through various stages in the F box along with the subkey, and then XOR operation is performed with the left part. The resulting 32-bit is placed in right part, and the initial right part is now placed in the left. The procedure is repeated 16 times, followed by the final permutation step. In the F box, we implement the following steps, as I'm going to discuss now. Briefly, it starts with key transformation, where we left shift the 56-bit key and eliminate certain 8 bits. For example, in the first round, the key will be left shifted by 1 bit, and we will drop the following bits: 25, 35, 38, 43, 54, etc. Then we implement the expansion permutation. For the right part, we create 8 blocks, each with 4 bits, then add 2 bits to each of them, resulting in 48-bit text. This part is now XORed with the 48-bit key, as we can see here. By the S-box substitution, the resultant 48 bits are then converted back into 32 bits. Then in the P-box, we perform a P-box permutation in the following pattern. And then again, the resultant bits are XORed with the left part and is placed in the right place for the next algorithm. After 16 rounds operation and final permutation, we get the ciphertext. As we can see here, we perform the final permutation in the following way. We place the 40th bit at the first position, 8th bit at the second position, and so on. And at the last, we get the ciphertext. Now let us come to the Verilog code part. We have a total of 2 modules in the Verilog code. In the process key module, this is a function where we generate subkey for 16 rounds. At first, we are generating the 56-bit permuted key by discarding 8 bits. As we can see, in the first position, we are putting 57th one. In this way, we are permuting the input encryption key. Then we are performing the left shift circular shifts with this function for 16 rounds. As we can see here, for 16 rounds, the number of left shift will be different depending on the number of rounds. Then we perform the 56 to 48-bit conversion via this function. And in the always block, basically we are calling those functions one by one. And it will happen 16 times for the 16 rounds. We are generating the subkeys for all the 16 rounds at this function. Then we perform the 56 to 48-bit conversion via this function. And basically in the always block, we are calling those functions one by one. And it will happen for 16 times for the 16 rounds, which will be the subkeys for those 16 encryption rounds. Now let us come to the main module. We are performing the initial permutation via this table. This is the initial permutation box. Then we start the expansion permutation via this function, starting with expansion for converting 32 to 48 bits, followed by the substitution box for the next part of our F box. In the S box, we are converting 48 bits text back to 32 bit. For example, here we are using the table ID to find the corresponding row number by I and column number by J, and then extract the data from S box. The P-box permutation is done via this function, and at the last part, the final permutation is performed here. After completing 16 rounds, final permutation is done by this function, and in the F functions later on, we basically perform all the mentioned steps in the previous part of our presentation. In the always block of our main module, basically we are calling all the functions one by one. Now we will explain the self-checking test bench here. We are basically putting different values for our encryption key and message and checking them with the result from an online website. For example, here in the last case of our test bench code, we have provided hello AAA at the message and a 64-bit encryption key. We have provided the ciphertext here, and if our ciphertext matches with the original result, then it will display encryption successful, and otherwise it will display error. We will check the result with this website. We will click on encrypt, and it has shown the result. Now we will match it with the waveform in our code. This was the third of our test bench code. We can see that the cipher text 5202FC41 matches with our desired result. We can also see that in the output we have displayed encryption successful.
Now, I will explain the backend design part, that is the physical design part of our project. First, we have completed the RTL design. RTL verification helps us to debug the RTL design and pinpoint problem and their solution. It saves the clock cycle and time of simulation. Here you can see the schematic view of our design. We needed a total of 10,350 gates in the process. Now comes the final stage, which is physical design. CADENCE Incisive implementation system will be used for that purpose. Following the instruction of the lab sheet, we have built the physical layout first, which describes the position of cells and routes for the interconnections between them. It was done in 8 steps. Design, import, and timing mode setup. First, we need to import the synthesis netlist. The purpose of the step is to import following items and bind them to the design. Next comes floor planning. Floor planning is the area budgeting of the chip. We can specify floor plan in 2 ways: by specifying aspect ratio and co-utilization ratio, by explicitly specifying the width and height of the die and core. After that comes creating power mesh. To make sure power uniformity throughout the design, separate power stripes for VDD and bases need to be created in higher metal layer. Then comes placement. Now we need to place the standard cells in the design and optimize placement. Tool optimize cell placement following minimizing congestion and while length. Next comes clock tree synthesis. Now we need to synthesize the clock tree for this accumulator design. To do so, first we have to set clock route and clock tree settings. Running nanoroute. Though timing is already closed in this design, we need to know nanoroute approach. In general, timing is not closed on design unless crosstalk is prevented. Analysis and then fixed. To really achieve the above, the design is run with global and detailed routing using nanoroute. Post-route timing and ASIC optimization. The design is fully routed and timing analysis should be run to analyze timing based on the actual routes. At the Innovus prompt run post-route timing analysis to report any setup or hold violations. After that comes adding filler cell and metal filling. In order to avoid DRC errors later, it is usually a good idea to place fill cells to fill in the gaps between our placed standard cells. This also provides mechanical stability and substrate uniformity on our chip. And lastly, we have done the exporting data. In this stage, we export GDS and netlist to run DRC. After successfully exporting the data, we checked the DRC result. We didn't find any error and the log looks like the following. Here you can see our results. So that was our presentation. Thank you.